Today, Sumegha, Garg, tell us about the space complexity of the point problem.
Yeah. Thanks for inviting me to the workshop. And then today we'll talk about a joint work with Mark and Orr, which investigates the space complexity of the coin problem. So what's the coin problem? It's you are given a biased coin, which is biased either towards heads or it's biased towards tails, and you want to figure out which way it is biased using independent coin tosses. Let's parameterize the problem a bit. So the biased coin, the bias of the coin is bias at least delta. So either it's heads with probability at least half plus delta, or it's heads with probability at most half minus delta. And then you are given n independent coin tosses, and you want to figure out distinguish between these two cases with probability at least, let's say 0.9 or some large enough constant probability. And now the question is that if you have n independent coin tosses, what is the bias? What is the minimum bias that you can distinguish? So it's not that hard to prove using Chernow bounds and stuff that you can statistically distinguish biases for which are greater than 1 by square root n, and it's like statistically indistinguishable when the bias is less than 1 by square root n. So this is the threshold above and below which it's just statistically not possible. But as we know, statistical distinguishability is not equivalent to computational indistinguishability. And one of the optimal distinguishers for this, solving the coin problem would be if the majority of the coin tosses were heads, you say it was biased towards heads. And if it was tails, you say it was biased towards tails. And this is the optimal distinguisher. But then computationally, for many natural computational models, majority cannot be computed. For example, AC0 circuits, which are constant depth polynomial size circuits, or AC0 circuits with parity gates, or some other computational models. So here now, because of its connection with majority function, coin problem has many uses in complexity theory. So to prove hardness results for various natural computational models, or because there is this inherent randomness in the problem that you have a biased coin which is biased with half plus delta, and you are getting independent tosses. It's also used in pseudo randomness. So the hardness results and pseudo random results are for various computation models, for example, small depth circuits, restricted branching programs, and recently it was also used to prove hardness results of streaming algorithms. Okay, so in this talk, we will the computational resource that we'll care about for the coin problem would be memory. So we want to figure out how much memory is needed to solve the coin problem. And when we are basically imagine this scenario in your mind, you are tossing the coins, and then you can think of it as like you're getting a stream of coin tosses. So once you toss a coin, unless you store it somewhere in the memory, what was whether it was heads or tails, it is lost, that coin toss is lost to you. So this can be, you can think of it as this model is that the coin tosses are arriving to you in a stream, and then you want to figure out with low memory what is the which way the coin was biased. Okay, so what is like some algorithm that, and what's the memory for what can be the lowest memory you can think of for solving the coin problem? Yeah, so you can solve it in log n by just counting. You count the number of heads, you count the number of tails. This requires log n space. And then basically after you count, you can just compute the majority, and that's like optimal. So counting takes log n space, and now the question is, can you do better than this? So let's look at some algorithms. Let's say you want to solve it in log k space, where k is some number less than n. Your first attempt would be, what you do is you keep track of the sum. What I mean is you keep track of the number of heads minus the number of tails, and then whenever it crosses k, if it crosses k, if it becomes greater than k, you output that it's heads, if it's biased towards heads, and if it crosses minus k, like it becomes lower than minus k, then you say it's biased towards tails. And now this algorithm works. It can distinguish coins with bias 1 by k, and it cannot distinguish coins with greater bias than this. So this is like, for example, if k is square root n, then this basically gives you the optimal algorithm, but that requires log n space. And now the question is this the best you can do? Is this the best a log k space algorithm can do? So in 1970, Hellman and Cover proved that yes, it is the best you can do if your algorithms are time invariant. So that is basically you have an automata, and then you're looking at like how many number of states an automata needs to solve this coin problem. So if a streaming algorithm is time invariant, then you need log k space to detect biases of 1 by k. In this talk, we will look at time variant streaming algorithms. So basically, you can do much better in memory if you have access to a clock. That means that you know which numbered coin, which numbered toss you're reading, and just this information lets you save on memory. So one of the motivations for this, like there are multiple motivations for studying this computation model in like practical applications. So for example, maybe you just have access to a clock in the computer, and that is an approximation for what numbered toss you're reading. Or if you are looking at many tasks at the same time, then this is some common information that requires less information. So this is like so there are some various practical motivations for studying this streaming model, which has access to a clock and the memory that needs to keep track of this toss number, which is log n, is not counted in the memory needed. Okay, so this is from a practical standpoint, that there is this stream. We were talking currently about streaming algorithms that have access to a clock, but these kind of models are encompassed by read-once branching programs. That would be the focus of our that would be the computational model that we will focus on in this talk. So basically, read-once branching programs are well-studied computational models in complexity theory, and this would be and then these encompasses streaming algorithms with access to a clock. And we want to understand how do these computational models solve the coin problem. Okay, any questions till now? Yeah, feel free to ask questions. Like from now onwards, I will talk about this computational resource, which is memory, and this computation model, and this might be new to, I don't know, people with mathematical in mathematics. So please ask questions. Okay. And then we will see that for biases greater than equal to n to the minus 1 by 3, when you're talking about streaming algorithms, then only order log n memory suffices to detect these biases. If it was a time invariant, then you needed log n memory, but we are saying that only log n memory suffices to detect biases of n to the minus 1 by 3. And then the surprising thing is that there is a threshold at this this bias that you need log n memory. Even in this model of streaming algorithms with a clock, you need log n memory whenever bias is less than n to the minus 1 by 3. Okay. So let's look at what's this read-once branching program. So read-once branching program is a computation model which can be thought of as an acyclic graph. So you have n times w vertices, and the vertices are divided into n layers, and each layer has w vertices. And then the edges are present only from ith layer to ith plus 1 layer. And then when you look at a vertex, there is an edge labeled 0 that goes to a vertex in the next layer, and there is an edge labeled 1 that goes to the other vertex. This transition basically represents that if you are at this vertex and you read a 0, then you will transition to this vertex. And then if you are at this vertex and read a 1, then you will transition to this one. And So basically read once this when you transition through the program, this will become like a computational model. So you start at a vertex in the first layer, and then you read the input bits, which are, let's say, n bits. So you read x1, transition to the second layer, read x2, transition to the third layer, and so on. And then finally you will be in the last layer. And then there is a green node, which is the accept state. If your computational path reaches the green node, then you say that the output on that input stream is 1. Otherwise, you say the output on that input stream is 0. So this is the computational model. And then, yeah, any questions on the model?
You always start in the same vertex at the beginning?
Yeah. So yeah, so these vertices don't matter.
So how is this different from a decision tree?
So decision, so first of all, it's like a decision tree is a tree. This is not a tree. There can be different paths going to the same vertex.
Okay.
Yeah. So like 1 and 0 goes here, and then 0 and 1 goes here. So there's like
bounded width, right?
It's a bounded width.
Okay, done.
Yeah. So it's bounded width.
So it's to the space and not to the zero. Okay.
Yeah. No, yeah, I will explain that. So okay, so this is a read-once branching program. Now, if you have a space S algorithm, then space S algorithm that works on n input bits, then you can construct a read-once branching program that has width 2 to the space and length n. So this is because if you have space S, then you can look at all the memory configurations. These are 2 to the S number of configurations, and then this transition basically represents like the change in the memory configuration after you read the input bit. Okay, so from now onwards, basically a space S algorithm would give you a 2 to the space width read-once branching program. So whatever we talked about, like log n memory would correspond to log n width read-once branching programs, or log n memory would correspond to n width branching programs. So from now onwards, we will just talk in terms of width. Yeah, and I won't do these calculations of like converting the memory and width. Okay, so what is known for point problem in ROBPs? So counting works, as we saw before. Counting works whenever the bias is greater than 1 by square root n, and this corresponds to a width n read-once branching program. And then by various constructions, it can be shown that even constant width read-once branching program suffices to detect biases of 1 by polylog n. So whereas if it was time invariant, you would need at least log n width, but here you're saying that even constant width suffices for detecting 1 by polylog n biases. And then so I will talk about this construction a bit later, but to give a prelude, this construction uses read-once Boolean formulas, and using similar ideas, you can get order log n width read-once branching program for which detects biases of 1 by n to the 0.3. So already with like known literature, we can detect biases of as less as 1 by n to the 0.3 with just log n width read-once branching programs. And then what about lower bounds? So lower bounds, so there are these papers that have shown that you need at least approximately log 1 by delta width if delta is the bias for read-once branching programs. And then there was in 2020, this paper showed that you need at least n to the like at least polynomial in n width when if the bias is 1 by square root n. And then the question is what happens in the middle. And then so our paper showed that counting is basically optimal for biases less than n to the minus 1 by 3. So you need polynomial in n width read-once branching programs if the biases are less than n to the minus 1 by 3. But if it is above that, then order log n width read-once branching program suffices.
So just to clarify, so that if your bias delta is more than 1 over the 1/3 reads, the answer is log 1 over delta. Right. This is what you said before.
Yeah.
And this is tight. So this is the one of the tight for the entire regime.
Yeah, so it's like log 1 by delta divided by log n divided by log n. So I think there is still like, yeah, you can maybe improve a bit on it, like, but I think it's tight. Yeah. Like up to order fact, like if you are considering memory, then it's tight, but if you're considering width, it's not tight. Exactly. Okay, great. Any other questions?
I might have missed something. Is the randomness just coming from the randomness, the algorithm?
So yeah, I guess it doesn't matter because you can choose one randomness that works because like it's a non-uniform model. Read once branching program is a non-uniform model, so it doesn't matter. But yeah, so for now, let's assume it's deterministic. Okay, so let's look at the upper bound. How do some techniques for proving the upper bound? So we will look at this tribes function. So this is basically, so you want OR of AND. So you have n sized input, x1, x2, xn. You divide the input into m sized blocks. So this is m, and then there are like n by m blocks. And then you do an AND on this, on each m sized block. And then finally you do an OR. So this is the tribes function, and you think of m as like log n size. So basically you're trying to find a log n sized block that such that all of the inputs, all of the inputs are 1, and you want to see if there exists such a block in this function. So basically you're trying to, if the intuition is that if the bias of having a 1 was large, then you will find such a block that like that will contain one log n size block such that all of the input bits are 1. So this is a tribes function, and basically one of the fact about this function is that when each bit of x is 1 with probability at least half plus 1 by log n, then the output of this tribes function is 1 with high probability, so like with constant probability. So this is like so one, you can think of this as like basically if my bias was if these were biased by 1 by log n, it's amplifying the bias to a constant probability. So it's like a gadget that amplifies biases of the input. And then basically this is also a function that can detect biases, that can detect coins that have bias 1 by log n. And now that means that it can distinguish whether the coin was biased towards 1 or 0. Okay, so why is this nice? Because the tribes function gives you a with 3 length and read once branching program that detects a bias of 1 by log n. So let's look at this read once branching program. So again, the read once branching program is that you have n layers, and then each, because it's with 3, so each layer has 3 vertices, and then we will color to understand what each vertex in the layer represents. Let's color code them. Green vertex basically represents that you have accepted the input at some point. Red vertex basically represents that for this m sized block, you are trying to compute the AND of the function, and then brown represents that for this m sized block, the AND is 0. So these are the, so each layer has 3 vertices like this, and then you start at a red node, and then if you keep seeing 1, that means that you still have the chance that the AND of this m sized block would be 1. So you keep seeing 1, and after m m time steps. If everything was 1, you say that you are accepting this input. And then if at any point you saw a 0, you move to a brown colored vertex. And then whenever after m steps, after m time steps, it's time to now compute the AND on the next sized block. So you move again to this red vertex. So note that this thing cannot be done for a time invariant function. So you really need to know when you have read m tosses to make this transition, that you need to compute the AND at the next time step. So this thing basically gives a read-once branching program the strength to detect biases of 1 by log n with just with 3. No. So 3 is related. No, I will tell you what 3 is related to. Okay, good. Any other questions? Okay, so as I told you, it's like you can think of it as just like amplifying biases. Like instead of like detecting 1 by log n, if it got a bias of delta which is less than 1 by log n, then it just amplifies to log n times that delta bias. So you can do recursive tribes, which will imply a width w length and read-once branching program that detects biases of 1 by polylog. So this gives a constant with read-once branching programs detecting 1 by polylog biases.
Why can you detect that width to be log n in this formula?
Yeah, so you cannot. If there is at some point you like the errors accumulate and then it does not work. Okay, so more generally, what we are doing is we are identifying a bias amplifying gadget, and we are recursing. So in the previous few slides, the bias amplifying gadget was the tribes function, but now maybe we can choose some other gadget and then recurse on it. So let's say we still want the gadget to be a read-once Boolean formula. Then let's say phi is a read-once Boolean formula that amplifies bias from delta to alpha times delta. And I want to say that the example that I give here is the optimal read-once Boolean formula that amplifies optimal bias. So this just results in an AND or tree. So this gadget is this. So it works on it's 4 sized, that it works on 4 input bits, and then you are recursing on it and basically making an AND or tree. And then if this is the property that if you have S sized formula that amplified alpha, what you can do is, because you in the end you have n input bits, you can recurse till log n by log s times. So that is the recursion depth. And then each time you're amplifying the bias to alpha times that, so you get the amplification to be alpha to the log n by log s, which for this formula gives you n to the 0.306 times delta. So basically an AND or tree can detect biases of 1 by n to the 0.3. Yeah. Oh.
What's the amplified read-once program?
Wait a minute. So now this is just a read-once Boolean formula. I was talking about a read-once Boolean formula, yet so it's like an AND or tree, and that's the amplifying thing. But now you use this connection that read-once Boolean formulas can be implemented by read-once branching programs with width equivalent to the depth. And then because the depth is just log n, so here you are getting a read-once branching program that is amplifying biases by a factor of n to the 0.3, so basically it solves the coin problem.
Sorry, is this recursion thing that is at the bottom, is that the same as the recursive tribes that you said on the last slide?
Yeah, so in the recursive tribes, you're recursing on a tribes function, which is like this and of like or is bigger and is smaller size. But here you are recursing on this function of or and of and.
Okay.
So it's like basically I'm saying that you can recurse on any bias amplifying gadget, and that would be an idea that we will use. So here our bias amplifying gadgets are read-once formulas, but from to improve on it, we will use a read-once branching program as the bias amplifying.
I see. But I guess this is like tribes with like m equals n equals 2 or something, right?
Yeah. Does it answer your question?
Yeah.
Okay. So now the interesting part is with read-once branching programs or with log n, we can even amplify better. With read-once Boolean formulas, this is the best you can do. But read-once branching programs, you can do n to the 0.33 times delta. It might seem like a small increment, but as we saw, it's tight. So that's the nice thing. Okay. So let's talk about like this. So on the previous page, I told you that a read-once Boolean formula can be simulated by read-once branching program using width equivalent to the depth. So this is a non-trivial fact, but it's folklore. And then let's see a high-level idea for how to simulate a read-once Boolean formula using a branching program. So you're given a read-once Boolean formula of depth d, and then basic recursion would be like you look at the top and you try to compute both the answer to both the subtrees. So basically you are storing in this recursion, if you think a bit about it, you're storing a bit for each depth. Like you will be working on one subtree, you're storing the answer for the other subtree. So you're storing a bit for each depth. So this will correspond to a D memory algorithm. Because you're storing D bits, and if D is the depth, so which corresponds to 2 to the D width read-once branching program. But here we are saying something very strong. We are saying that it can be simulated by just a D+1 width read-once branching program. So how do we do it? So let's look here. So this is basically the AND OR tree, and in the a read-once branching program, I am representing length is still n, and for width I'm representing a vertex in each layer for every depth of the read-once Boolean formula. So there is a vertex for the bottom layer, for the leaves, and then there is a vertex for the depth 1 vertices, and so on. And then how I compute this read-once Boolean formula using a read-once branching program, I look at the first input bit, and I start here. So if this input bit is 1, then I know that OR of this subtree is 1. So I don't really need to read this input. Whereas if you were doing basic recursion, you will not use this fact. You will still read this input and try to compute the OR finally. But here, because it's an AND OR tree, for one answer, you don't really care about what the answer of the next input bit is. So basically, you then for the next layer, you move on to this vertex, that is like you are at depth 1. And whenever we are at a vertex which is not depth 0, we don't care, we don't read that input bit. And then, so this is 1, but being this subtree being 1 does not tell you what is the AND of this subtree. So you need to compute this subtree. So what this means is that, and you know at what time step you need to start computing this next subtree. So you move back to the bottom position and read this input bit. So let's say it's 0. This means that the OR of this subtree still depends on this input bit. And then you read 0. Let's say everything became 0, and this AND is 0. Now, if this subtree is 0, then still for computing this OR, you need to figure out the answer of this subtree. And then again, you go to the bottom. And then you keep doing this. So basically, I've shown you how to compute a read-once Boolean formula by just using width D+1. Any questions? Yeah, maybe, yeah, I can pause here for 1 minute. Okay. So, okay, so even if you didn't understand this, I want to point out one characteristic of this simulation, that is that for every layer of this constructed read-once branching program, there is only one vertex for which you are actually going to read the input bit. For any other vertices, you don't care, irrespective of what is the next input bit, you're going to transition to the same vertex in the next layer. So only for one vertex in each layer, you actually care about what is the input bit and will transition according to that input bit. So this is a concept that we'll define, is called the effective width of a read-once branching program. So the width of the read-once branching program can be anything, but the effective width is 1 if for every layer, for all but one node, the transition to the next layer is independent of the input bit. And why is this good? Because when we recurse on read-once branching programs with effective width 1, then width increases linearly with depth instead of exponentially, because there is only one node that is expanding again and again. So it's a linear growth instead of a exponential growth.
So the idea, just to make sure, is like, instead of doing the recursion in the formula, you just convert the formula to the branching program once and then do the recursion in the branching.
Yeah, so that would be, so that happens. Okay, so this is the reason why it grows linearly. If you convert a read-once Boolean formula into read-once branching program, then you have a way to convert it in terms of like the effective width is 1. So if you recurse on it, the depth only increases by 1. But that is just one way of constructing read-once branching programs for solving the point problem. But here I'm saying that like maybe you can develop other read-once branching programs which have effective width 1 that solve the point problem and then recurse on them. Because the read-once Boolean formulas can only take you till 1 to the n, 1 by n to the 0.3. It cannot improve on that. Okay, so this is the gadget that we use for the upper bound. The gadget is let r be a constant. Then we construct a length r to the 3 by 2 width r to the 3 by 2 read-once branching program with effective width 1, such that amplifies the bias of square root r. Now, I think these are some constants that you wouldn't appreciate right now, but let me talk about another problem from now onwards, which is related to this. So to solve this gadget, we look at one mathematical object and show the tightness for that mathematical object, and that gives us the bounds for the point for the read-once branching programs for the point problem. So let's not worry about these lengths and widths and amplifications yet. Let's look at this mathematical objects of sequences capturing random walks. So if I lost you till now, this is this part of the talk can be of independent interest. Okay, so here now we want that we have this sequence of integers a1 to al, and then we are getting these random walks, and so you have you want to do a r length random walk, and then you want this sequence of integers to satisfy some properties. So you want that with high probability, the random walk that you do, like for example, b1 plus b2, b1 plus b2 plus b3, and so on, it's actually a subsequence of a1 to al. So what do I mean? So we write it in this sequence. So it's very important. It's a sequence, it's not a set. So A1 to AL is written like this. And then you do an R length random walk. Let's say the first bit is B1. Then you move to A1, and basically A1 is equal to B1. Only then it's valid. And then you read B1, B2. Then you want that A3 is B1 plus B2. And then you want AI is B1 plus B2 plus B3. So basically you go on like this. So the random walk that you're doing, like wherever we are stepping in the random walk, that sequence should be a subsequence of this A1 to AL, and this should happen with high probability over all R length random sequences.
Done. So the BI is just random bits. So B1 plus B2 could be the same as B1.
Yeah.
So you're okay with going to the same number?
No. No. So first of all, B1 plus, I'm thinking of B1 and B2 as my 1 minus 1. So that cannot happen. But yes, so the sequence, so B1, yeah, you should only go forward. So it's a subsequence. So if B1 is here, then you go to something that is in future, B1 plus B2, and then you keep on going in future. You don't understand? Okay.
The BIs are plus minus 1.
Yeah.
How is the BI connected to the AI?
No, so I'm saying that AI is a fixed sequence, and then with high probability, when you take B1 to BR as random bits, it should be a subsequence of A1 to AL.
The sequence for the sums of the prefixes.
Yeah.
And you said it's only valid if B1 is A1, or was this just?
No, so that, but yeah, I think it would be easier to do it like this. So these are the random bits. Now basically, I'm doing random work, right? So I start at 0, then I do 1, then let's say 2, then let's say 1, 0, minus 1. So this sequence 0, 1, 2, 1, 0, minus 1. This sequence that you get should be a subsequence of A1 to AL. Did you answer the question?
Yeah.
Okay. So I think once you see an example of such a sequence, it would become more clear. So why is it interesting? So now we want to find the smallest L for which this is true. That you want to, it should be subsequences of A1 to AL, and then you want to find the smallest L for which is true. Let us give an upper bound. There exists a R to the 3 by 2 length subsequence, a sequence such that this statement is true. So what is the sequence? It's you take minus square root R to square root R times. So with high probability, a random walk does not cross square root R. So there is always a subsequence. Basically, because you're doing R times, there is always a subsequence for whenever B1, any of these, whenever you don't cross square root R, there is a subsequence of these numbers corresponding to that random walk. Okay. So this is an upper bound, and then this is the fact that we use in our upper bound. We say that this implies a length L, width L, read once branching program with effective width 1 and square root R amplification. Basically, because you're working with random walks, you're getting optimal amplification, which is square root R. And because of this nature of this, that you're only skipping forward, it gives a read once branching program with effective width 1. And that is what we needed for recursion in this. So let me tell a bit about this this reduction for people who are interested. Okay. So this means that you have R to the 3 by 2 sequence such that this is satisfied. So what you do is you have L length, L width. So each vertex, there is a vertex for each AI, A1, A2, and then ith layer means that you are at AI. Basically, like the random walk has reached AI. So whenever you are at AI, only at that point you need to read the next bit and figure out what is your next goal. Like what is the next AJ greater than AI that you want to reach. So basically you start with whatever 0 or something. Let's say A1 was 0. And then let's say it said forward to A3. Then you reach A3, the third layer, and then you read the next bit and so on. So this is effective with 1 because only for the ith layer, only if you are at AI, then you will read the next bit. Yeah, so that's why you need bit L. You will have that information that you are jumping several forwards. So there would be like, are you jumping to forward AJ? Are you jumping to forward AJ plus 1? So there would be, it would be stored. This information would be stored because it's a constant. We don't care about this. Okay, so the thing is that it's effective with 1 and it needs R to the 3 by 2 length. And then why does, now here is where 1 by 3 comes in. So now because one gadget uses n to the 3 by 2 inputs, so you recurse for log n by log R3 by 2. And then because you are amplifying each term by R to the half, so you get this total amplification, which is n to the 1 by 3. So this is where 1 by 3 is coming from because it's square root R and R to the 3 by 2. It uses R to the 3 by 2 input bits.
Can you remind me, where is the root R amplification coming from?
So the root R amplification is, I think, it's basically, it's coming from that most of the random, like it's anti-concentrated, the random walks are anti-concentrated. So basically you will have this, even when you're taking root R steps, the steps that take, the random walks that take root R steps, they should be in this sequence. And whenever you reach a root R, then you have detected bias of root R.
Do the lower bounds for coin problems imply that this is optimal?
Yeah. Okay.
Can you explain again why you can get into the 1/3?
Yeah, so it's because each gadget take R to the 3 by 2 input bits. So then you are recursing from log n by log R to the 3 by 2 steps, a depth, and then each amplification is R to the half. So you get R to the half of this. And then, yeah, you can do the calculation. It's n to the 1 by 3.
So you still need to recurse it because you want to close it down.
Yeah, no, because then the bit would be too high. Bit would be n to the 1 by 3. So you need to recurse. That's why I think that's the important thing. You need effective with 1 so that recursion only increases linearly with depth.
And effectively get like you lose some constants.
Yeah, because it's just like it would be like maybe yeah, it won't be n to the 1 by 3. It would be like some maybe the log n plus some constants, like order of n to the 1 by 3 plus. Okay, great. So now the thing is that this is optimal. You cannot do better. L is omega R 3 by 2. Now, why is this useful to us? Is because a length n with W read once branching program that solves the point problem for delta biased points gives you something which has L W times n and R random walks of 1 by delta square. Yeah, here like basically there is like this like square root R bias amplification. So that's why there is this. So this means that if you use this theorem, then this means that W times n should be greater than 1 by delta cube. And then if the delta cube is just like delta is less than 1 by n to the 1 by 3 minus epsilon, then this tells you that the width should be polynomial in n. So it should be greater than n to the epsilon. So yeah, so the lower bound can work for less than 1 to the n to the 1 by 3 minus epsilon. Okay, so yeah, I think this is this proof is a bit involved. So you need to basically to just say a couple of lines about it. So you basically analyze the read once branching program and the probability of success at each step, and then you say that the probability of success basically is a random walk, because if you see a 1, then you are going towards heads with probability with bias, like you are improving towards you're improving your probability of success by delta, otherwise you're decreasing your probability of success with minus delta. So it's like a random walk, and then you have to do some calculations to say that the merging in the branching programs don't help. So basically this is the only way you can find a read once branching program for amplifying biases. Okay, great. So in the last slide, I want to say a bit about like why this statement is true. So we proved this theorem that L needs to be at least R to the 3 by 2, and then use it to get a lower bound for read once branching program. So what you do is you take some 0.01 R points that are doing the random walk. You basically want to prove that because the random walks are anti-concentrated, so you need a lot of points. You need L is R to the 3 by 2. To prove such a statement, you say that you are taking these many points, and then you are making them do the random walk, and then you see what are the distinct sums that they will hit. So they hit total n times R points, because each point is doing R length random walk minus the collisions. Now, because it is a random walk, then you can argue that each 2 points collide only square root R times. So that means that L needs to be greater than n times R minus n square times square root R. And for right parameters of n, you get this lower bound. Any questions? Okay, so I think with this, and the last thing I want to mention is like one of the open problems would be like if you have multiple passes over this coin, if it's like read twice or like 2 pass read once branching program, then does this threshold still remain, like or does the threshold change at which the low memory algorithms exist? Okay, thank you.
Question?
So the question is that if you have multiple passes over the stream of coins, then does this threshold hold or not?
What do you think?
I think it should hold because
The same.
yeah, the same.
Like you think about constant number of passes.
Yeah, constant number. I'm thinking about constant number of passes. Well, do you?
Like if you have like log n passes, then you're done, right? Come trivial.
What?
That's interesting. Yeah, maybe login. Yeah, maybe like even like login number of passes. Maybe yeah, I'm thinking of constant number of passes for now.
So from this delta equal to n to the 1/3, was there an abrupt jump from log and weight?
No, I think there should be actually a smooth jump. Like so, we prove it for like constant things. Like it's like n to the minus epsilon and n to the minus plus epsilon. So this is like constant. But so basically, if epsilon is a constant, then there is a jump. But I think between that there should be smooth.
So you can check the model a little bit. If you first draw, let's say you first toll the coin n times, get n flips, and then you draw with replacement from the flips. And each time you see a random flip. So most flips you see, you only see it once. But for some flip, you see it multiple times. Like in this model, does the same bound still hold? Also, I'm thinking about something like a bit like coupon collector, but
It's the same, but once you fix the random to sample, and then you sample from each randomly for replacement, it's sort of like sampling from a slightly different delta, like empirical delta. Because you have to do sample, which should be about the same.
oh yes.
Okay, that's it. Okay.